In Chapter 4, we are getting into chemical equations and stoichiometry. So the chemical equation describes a chemical change. The left side of the arrow has what you start with. That's known as the reactants, or also the starting materials. Sometimes I call it the starting materials. And then the right side of the arrow has what you end up with, which could be called the products. The chemical formula for each compound or element is written in the chemical equation on one side of the arrow or another. And next to each compound, each chemical formula, you should include the physical state. It could be a solid, a liquid, a gas, or it could be dissolved in solution in water. Aqueous solution means that it's dissolved in water. A lot of reactions take place that way. The coefficients are the numbers you put in front of the chemical formula to indicate how many of each thing you have. Because of the law of conservation of matter, you need to have the same number of each element on the left side as on the right. And making the equation agree with that law is called balancing the equation. So you should not balance an equation by changing the chemical formula of something. So you cannot change water from H2O to be H2O2. If you have water, it should be written H2O. Let's say it's a liquid. If you have another oxygen in there, you can't balance it by writing H2O2 because that is not water. So make sure you have the correct chemical formula before you start to balance an equation. And then a good start is to count each atom, or count how many of each element you have on each side. And then if you do not have a match, you can put different coefficients, increase the coefficients in front of the compound so that you can have more of the elements that you need that are inside that compound. If you go back and forth too many times, you might find that you do not have the simplest ratio. So you might have 2, 4, and 2 as your coefficients, and that can be simplified. You can divide each of those by 2, and you end up with the coefficients 1 to 2 to 1. We have a few tips down here that might be helpful. I think just practicing doing some of these is the best way to learn how to do it. A lot of people I find do remember from previous chemistry courses how to balance an equation. I think this is one of the more memorable topics that people have studied before. I do want to point out that combustion is sometimes one that students find the trickiest. And so what I do is go forward. So combustion, I go forward with the carbon and the hydrogen, and I save the oxygen for last. And then since oxygen comes in pairs, if you need an odd number of oxygen atoms, you might find yourself needing 2.5 or 3.5 oxygen molecules. And I put that temporarily, so I put that 2.5 or that 3.5 temporarily, but then I go through and double everything so that everything can be a whole number. So let's go ahead and try balancing this chemical equation. The formulas are already written correctly for you, so you don't have to worry about that. So the next thing is to make a list of the elements that are in this reaction. It's not a very long list for this one. We have nitrogen and hydrogen, and I wrote a list on the left and a list on the right. On the left, we have 2 nitrogen atoms and 2 hydrogen atoms. We're starting off with no coefficient, and if there's no coefficient, it's assumed to be 1. One ammonia molecule would have 1 nitrogen and 3 hydrogen. Okay, this is not balanced. We don't have the right numbers. They're not matching. So what we need to do is increase the number of nitrogen. We can do that by putting a 2 in front of the formula. We don't change the formula to N2H2. That's not ammonia. So we put a coefficient in front. That changes this. We now have 2 nitrogen, and we now have 6 hydrogen. Our nitrogen is balanced now, but our hydrogen is not. So we can try putting a 3 in front of the hydrogen, and that would give 6 hydrogen atoms on the left. Now it is balanced. We have a match between the number of things on the left and on the right. Let's try doing the next one. So on the left we have 1 mercury and 1 oxygen. On the right we have 1 mercury and 2 oxygen. I usually like to keep these in the same order just because it's easier to see the match. So since I had mercury written on top over here, I kept it on top over there. Okay, but we don't have enough oxygen on the left. So let's go ahead and increase that. We'll have to put a 2 in front here. That increases our oxygen, and it also increases our mercury. So now we're going to need more mercury over on the right. So we'll put a 2 over here, and that increases our mercury. And so now we have a match for both of the elements. For this chemical reaction, I wanted to point out that if you have a polyatomic ion that stays the same on both sides of the equation, so this sulfate group stays the same on the left and on the right, you can balance the sulfate as a group if you would like. So let's put what that would look like. On the left we have right now 1 aluminum, 1 magnesium, and 1 sulfate. But on the right we have 2 aluminum, 1 magnesium, and 3 sulfate. Alright, let's go ahead and increase the magnesium sulfate. Let's put 3 of these so that we can have the 3 sulfates that we need. Now we're going to have to increase the magnesium. So we'll put a 3 in front of the magnesium. That makes 3 magnesium. And now we just need more aluminum on the left. Aluminum's all alone, so that's pretty easy to increase without messing up other things. And now we have a balanced equation here. If you had wanted to, you could just balance the sulfur and oxygen separately. Let's take a quick look at what that would be like. So if you prefer to balance the sulfur and the oxygen separately as separate elements, this is what it would look like to start out with. We still need more of the sulfur and oxygen, and since we need 3 sulfurs, I'll go ahead and triple this. That brings the sulfur up to 3 and the oxygen up to 12. So we have some matching sulfur and oxygen. We still need to increase our magnesium. And then finally we need to increase our aluminum on the left. So we come up with the same result for our balanced equation. These next two give a little practice with combustion reactions. We have a fuel and oxygen going to carbon dioxide and water. So here we have another combustion reaction just with a different fuel. So the fuel is different, but all combustion reactions have oxygen as another starting material, and then the products are CO2 and water. Okay, to start out with, we have 3 carbon, 8 hydrogen, and 2 oxygen on the left, 1 carbon, 2 hydrogen, and 3 oxygen on the right, 2 here and 1 here. So for combustions, I go from left to right first, balancing the carbon. So to get 3 carbon, I'm going to need 3 CO2. That makes this 3 and this 7. Now I'm going to go left to right with the hydrogen. If we have 8 hydrogen, that's going to make 4 water. So now our hydrogen has increased to 8 and our oxygen has increased to 10. We have 6 oxygen in our 3 carbon dioxide molecules and 4 oxygen in our 4 water molecules. So altogether we have 10 oxygen. Okay, our carbon and hydrogen are done, but now we need to figure out how many oxygen molecules we need. To get 10 oxygen atoms altogether, fortunately that's an even number, we would just need 5 oxygen molecules. So now we have this balanced. Okay, so let's try this next combustion reaction. Starting out, we have 4 carbon, 10 hydrogen, and 2 oxygen. So we'll go forward with the carbon. If we need 4, we need 4 carbon dioxide. That brings the carbon up to 4 and the oxygen up to 9. And then with the hydrogen going forward, to get 10 hydrogen, we need 5 water molecules, which brings the hydrogen up to 10 and the oxygen up to 13. So now we need to go back and figure out how to get 13 oxygen atoms from oxygen molecules. So we need 13 halves, or 6.5 oxygen molecule. Let's go ahead and put that for now. Now the last thing to do, we have this balanced. Oh, I didn't write this. Okay, we have it balanced, but the only problem is we have this fraction as a coefficient, so we should go through and double everything to get rid of the fraction. We double the 1 and make it 2. We double 13/2 and make it just 13. We double 4 and make it 8. And we double 5 and make it 10. So let's go through and make sure that all the elements are still balanced. They should be if we doubled both sides. But we now have 8 carbons on the left, and we also have 8 carbons on the right. We have 20 hydrogens on the left, and we have 20 hydrogens on the right. And we have 26 oxygen on the left, and our 8 carbon dioxide gives us 16. Our 10 water gives us 10. So we have 26 oxygen on the right as well. So it's still balanced, which makes sense because we doubled both sides, so they should both still be balanced. So these next problems test your ability to connect what is happening with a reaction the way it's written in a chemical equation form. So a lot of times when you look at a chemical equation, you can look at the description and figure out what it might look like. So here, let's just look at this first one, solid aluminum. So you can picture this as some kind of chunk of aluminum, or maybe some aluminum shot or aluminum powder. So we have some solid pieces of aluminum. We also have something that looks like water. There's magnesium sulfate dissolved in the water, but it looks like water. So we have something that looks like water with little chunks or pieces or dust of metal in it, not dissolved. And then eventually we have a different metal, not dissolved, and something else that's dissolved. So this reaction is going to look like some metal kind of sitting at the bottom of a test tube that has water in it, and going to another different metal sitting at the bottom of a test tube that has water in it. So sometimes this has this would probably go in the reverse direction actually. I'm not sure why I wrote it this way. So this reaction would really be driven this direction. The magnesium would be more likely to be reactive and the aluminum would be more likely to be sitting there. But that's kind of what this would look like. So how would we represent something where you have zinc metal reacting with, it's a solution of hydrochloric acid. I should have put that it's a solution. So we have an aqueous solution of hydrochloric acid. If we have pure HCl, I don't know if you remember from the naming, but pure HCl that is a gas is called hydrogen chloride. If it's dissolved in water, we call it hydrochloric acid. So we have an aqueous solution of hydrochloric acid, not just hydrogen chloride gas. All right, then we are forming zinc chloride, and it's dissolved, it's soluble. And then we are forming hydrogen gas, and these are going to look like bubbles coming out of the solution. So we are going to take a test tube that looks like it has water, put some pieces of metal in it, and the metal is going to go away. It's going to become something that's dissolved, and bubbles are going to come out. So that's what this would look like. What would this look like in equation form? So zinc metal would just be written zinc, and it's solid. Hydrochloric acid solution, we already have it written over here, HCl, and it's aqueous. Zinc chloride, so it's reacting, and now we're forming something new. So this is what we're mixing together. Then we have a change. This is where we put the arrow. It's changing. The new stuff that we have on this side includes zinc chloride. Hopefully you can write the formula for zinc chloride from your naming practice. It would be ZnCl2. And it is dissolved. It's not a solid, so we would write aqueous. It's dissolved in the water. Hydrogen is one of our diatomic elements. So hydrogen gas has the formula H2, and it's a gas, so we'll put G over here. So this would be the chemical equation for that transformation. Now that we have all the formulas written correctly, we need to balance the reaction. Okay, so the zinc is looking all right, but the hydrogen and chlorine, we need another one over here on the left. So let's put a 2 in front here. That will give us 2 hydrogen and 2 chlorine atoms, and so now it is balanced. Okay, so iron 3 oxide, and it's a solid. Here's the correct chemical formula for iron 3 oxide, and then we note that it is a solid. And then carbon, solid carbon would be written like this. That's what we start with. We put that on the left side of the arrow. When it changes, we've created carbon dioxide gas, CO2, and iron metal. So that would just be iron, and it's a solid. If you want to write heat over the arrow to show that you need to put heat into this reaction, you can. Sometimes we express that as a delta, a capital delta in Greek, which means sort of a change in energy or change of temperature. Heat has been added. So now that we've written the reaction, let's check and see if it is balanced. It's not balanced the way it is written yet, so we need to increase the iron and oxygen over here on the right. Let's go ahead and increase the oxygen first because it's in 2 different compounds, so we want to make sure that we have the right number of each of these compounds first. The carbon and the iron are all alone, so it's going to be really easy to change those numbers at the end without messing up anything else. So let's try increasing this to 2, and that increases our oxygen to 4. Now we have too much oxygen on this side, so we're going to need to increase this side. Let's increase this to 2. That gives us 4 iron and 6 oxygen. So now it looks like we're going to need more oxygen on this side. So instead of 2 carbon dioxide, let's put 3. That gives us 6 oxygen and 3 carbon. So you might have been able to reason this out, that if we need the same number of oxygen on the left as on the right, we're going to need 2 groups of 3 becoming 3 groups of 2. But if you didn't recognize that, you could just do it stepwise like I did. So now the last part is easy because we just need 3 carbons. It's all alone, so we can change this to a 3 and just get that to be the number we need. And then now we need 4 iron on this side. And that's also easy, just change that to the number we need. Okay, I scrolled up to give myself more room. We have a solution of lead 2 nitrate. So here's the correct formula for lead 2 nitrate. And we write aqueous because it is dissolved in aqueous solution. The formula for potassium iodide is Ki, and again we have aqueous solution. These are the 2 things we start with. They react, so we have a change. Now we have a precipitate. A precipitate is something solid that comes out of solution. It's no longer dissolved. So we have a solid precipitate. Lead 2 iodide would have the formula PbI2, and we put an S to indicate that it is a solid precipitate. The other product is potassium nitrate, and that is dissolved. It is soluble. The correct formula for potassium nitrate is KNO3, and that is aqueous. All right, I'm going to balance the nitrate together as a polyatomic ion because we have nitrate together on the left and on the right. It doesn't change. The nitrogen and oxygen don't separate from each other or become anything else. So we can treat it as a unit. Okay, so we have some mismatches as far as the number of things goes. We need another nitrate on this side, so let's go ahead and put a 2 here. Now we have 2 nitrate and 2 potassium. And we just need a little bit more potassium and iodine on this side. So we can put a 2 here as well. And that will increase our potassium and our iodine up to 2. Let's take a look at ionic equations. These are chemical equations that focus on the way the ions are separating when they are dissolved in water. So the way this reaction is written here is the more standard way to write a reaction. We're just looking at the compounds. We are not looking at the charges of the ions that make up this compound, but if we wanted to, we could take a closer look at those ions and figure out what is really happening in solution. The first step to doing that is to write the complete ionic equation. So anything where the ions are separated when they're dissolved in water, we're going to show them as being separated. So let's just take a note of what things we're going to separate and what things we're going to keep together when we write this ionic equation. And we want to reflect reality. So when we dissolve ionic compounds in water, the ions do separate. That's why we're going to write them as separate, because they do separate. Not everything separates when you dissolve it in water. Covalent compounds do not separate when you dissolve them in water. So if your reaction happens to have any aqueous covalent compounds, then we're not going to show them as separated into ions because they're not separated. Also, things that are not dissolved, solids that are sitting at the bottom of the test tube full of water, are not going into the water and separating. Anything that's a liquid or a gas is also not separating into ions. So there are some things that we want to keep together to show that they, in reality, are keeping together. So let's practice doing that. We'll write the complete ionic equation, which is sometimes called the total ionic equation. So these are the same thing. The complete ionic equation and the total ionic equation are two different names for the same thing. We have silver nitrate, and that is ionic, and it is also dissolved. So we are going to separate this into 2 silver ions and 2 nitrate ions. We have magnesium chloride, which is also ionic and also dissolved. So we are going to separate that also into a magnesium ion and 2 chloride ions. Now on the right side, silver chloride is ionic, but it is not dissolved. It is just sitting as a solid at the bottom of the test tube, and it is together. So we're going to keep it together. And then we have magnesium nitrate, which is ionic and dissolved, so it is separate. We're going to show it separate. So there is our complete ionic equation, or our total ionic equation. Everything that is separated is shown as separate. The next step is to decide which ions are spectator ions. They're just hanging around watching. They're not doing anything. So silver is doing something because it is different on the left than it is on the right. It is undergoing a change. It is not a spectator. Nitrate is not undergoing a change. It's the same on the left and on the right. It's just watching. So we're going to eliminate that. That's a spectator. Magnesium is also a spectator, the same on the left and on the right. Chloride is doing something. It's changing. So now we can write the net ionic equation, which eliminates the spectator ions that are not really doing much. And it shows what is really happening in this chemical change. And what is really happening is that 2 silver ions are meeting up with 2 chloride ions and forming 2 units of solid silver chloride precipitate. All right, let's start by writing the complete ionic equation, or total ionic equation, for this next example here. This aqueous ionic compound gets separated. This next one is an ionic compound that gets separated. This next compound is ionic, but it is not dissolved. It's not aqueous, so the ions are together as a solid at the bottom of the test tube. We'll keep them together. And then this ionic compound is aqueous, so we will separate it. So here we have the total ionic equation. Let's figure out which ones are the spectator ions. Looks like nitrate is not doing too much, and sodium is not doing too much. And the net ionic equation shows us what's really happening in this equation. barium ion and sulfate ion are coming together to form solid barium sulfate precipitate. Okay, so here we have an aqueous ionic compound, so it's separate. The next one is also separated. It's an ionic compound that is dissolved. The next one is also a dissolved ionic compound, so it's separate. And the next one is an ionic compound, but it is solid, so it's together. So here we have our total ionic equation, or complete ionic equation. The things that are not doing much are the potassium ions and the bromide ions. And the net ionic equation, the things that are changing, are that two hydroxide ions are coming together with a calcium ion to form solid precipitate of calcium hydroxide.